Hello, and welcome to episode 81 of the Sci-Fi Podcast. From Pittsburgh, Pennsylvania, I'm Nick Zautra. On today's podcast, I am pleased to welcome Dr. John Norton, Distinguished Professor in the Department of History and Philosophy of Science at the University of Pittsburgh. John is considered an utmost authority on the science of Albert Einstein and in the history and philosophy of science in general. He has published on a variety of topics, including general relativity, special relativity, the relationship between thermodynamics and information processing, quantum physics, and the genesis of scientific theories. He is well known for his analysis of Einstein's Zurich notebook, a small brown notebook which contains Einstein's private day-to-day calculations during a critical period between 1912 and 1913 in his development of general relativity. A central theme of John's work on Einstein is that Einstein's fundamental contributions to the old quantum theory have been largely forgotten because of his well-known criticism of the new quantum mechanics and its statistical interpretation. His latest work, The Material Theory of Induction, is the inaugural title in the new Open Access Series, the British Society for the Philosophy of Science Open, or for short, BSPS Open, that initiates a new tradition in the analysis of inductive inference. And thus, without further ado, let's bring in John. Dr. John Norton, welcome to the Sci-Fi Podcast. How are you this Wednesday morning?
Very well, thank you. How are you?
Doing just fine. It's a nice and sunny day here in Pittsburgh. Happy to be joining you this term in the in the Department of History and Philosophy of Science here. How's your semester getting on?
Oh, it's been going very well. I'm teaching the core seminar on philosophy of science to our new graduate students, and that's always exciting because they're excited to be here. And my job is to sort of usher them in, and I enjoy doing it. It's one of my favorite seminars to teach.
Wonderful, yeah. So. It's not, there's, quite a few philosophy departments, but not all of them, get to have a core seminar series. So in designing and in coming up with something like that, what goes into that in considering, how to teach the course?
Well, it's a difficult thing, figuring out just what is it that someone who's to be a professional in philosophy of science, what is it that they have to know? First, I should just correct you. We're not a philosophy department. We're a department of history and philosophy of science. So
of course.
We actually have 3 core seminars, one in philosophy of science, one in history of science, and a new core seminar in integrated history and philosophy of science, which is devoted to the question of how you bring the two together. So in the question of how do we put the seminar together in philosophy of science, the one that I'm teaching now, when I first started teaching it a long time ago, the plan was to make up a list of key topics. I inherited a syllabus from John Norton, who taught it before, and I went through looking at the basic ideas, and then there's only so much you can read. The idea was to read papers and discuss them, and so I developed a strategy of 3 papers. The idea would be to have one paper that was classic, right? So I don't know, Carnap or Hempel, then one paper that came from the Middle Ages, and then a modern paper that was maybe pointing the way to where things would go. So at the moment in the seminar, we started out reading the Vienna Circle Manifesto and Carnap's Testability and Meaning, and we've been following the empiricist tradition all the way through. We just read Nora Boyd's paper on enriched evidence.
Oh, wonderful! So getting right into the modern work. Great. All right, and so with the incoming graduate students, do they traditionally have quite a bit of philosophy of science background or history of science, or some do, some don't? What's your experience there?
We're not a philosophy department. If we were a straight philosophy department, we would simply be looking for strong qualifications in philosophy, and if you have it, then you get admitted. We're an HPS department, and so everyone in the department has some sort of eclectic background. What we're looking for are students who know some science. We've found that if you really don't have a good exposure to at least one science. It's very hard for you to do good HPS. And then we're looking for philosophical aptitudes, which normally comes out in philosophy or history of science courses that they've taken at some point somewhere. So it's a really mixed bag. And that's what makes it interesting, because you sit around the table and you have this huge array of backgrounds and expertise and interest, and it gets exciting because of that.
And I have to ask, so I know you're not teaching it this term, but so what went into coming up with this other course seminar, the integrated course? Has that been going on for a while? Is that
That was a new idea. For the longest time, we had one core course in philosophy of science and then two in history of science. And we began to see that the idea that history and philosophy of science is an integrated discipline was not really getting through. And so Mike Dietrich and I think it was Mike's idea to do this. Mike Dietrich is the chair, and then he recruited me to work with him on it. So we tried to figure out, well, what is it that you need to know to be an HPS person? We could really find no prior syllabus. When I did the philosophy of science course seminar many, many years ago, I first did it, I inherited a syllabus from John Norton. And that's a common thing. You find someone else's syllabus. We couldn't find anything like that. So we had to devise the whole thing from scratch. And that was interesting.
Very good.
The way it worked was we decided there was a core literature. And the core literature begins in the middle of the 20th century with all the stuff on scientific revolutions. That's really the core topic. So we're reading classic papers there. And then the next thing is the methodological issue. There's a way of doing HPS, or the way of doing this sort of investigation, that synthesizes history and philosophy at the same time. It's what I do. I do it all the time. And so we were looking for modes of that kind of integration of history and philosophy of science. We know lots of examples. And so we started working through all sorts of different ways that people do this, getting the students to look at how people are doing this. It was the first time we ran a seminar. How successful was it? It wasn't terrible. Can it be improved?
Sure. Yeah, absolutely. Yeah, no. Well, I'm familiar with the history and philosophy of science departments, and it is
from Indiana. Is that what you told me?
Yeah. So originally, got
the
training.
only other department of HPS in the country.
There's not many. There's the logic. There's a logic and philosophy of science department. There really, in the United States, in the mainland United States, I think there's only a handful, really. And probably even fewer actually core seminars in integrated HPS. I know there's special meetings that would happen at the PSA, to honor that, or there's other concurrence. But the kind of training one gets, it's will be interesting to see if more future students or future scholars will adopt this methodology and continue going forward.
There's a conference series for the Committee on Integrated History and Philosophy of Science. Don Howard and I started that around 2006. It's now in its 9th iteration. The symbol for it is ampersand HPS. I don't know if you've seen it.
Yeah. So
that is explicitly devoted simply to papers in integrated history and philosophy of science. It's in the name. That's what the big ampersand represents.
Is there a standalone journal for integrated HPS, or is it mostly no? Okay, be interesting if there ever was to be considerations for that. I know. I mean, there's their own. There's plenty of history of science journals or studies C, things like that. Which
Studies A, which is now just studies in history and philosophy of science.
That's right.
Has it? You asked about integrated history and philosophy of science. There are studies in history and philosophy of science is long established and has a tremendous amount of stuff. And you find there are plenty of other journals that are very hospitable to this kind of integrated work. I mean, I've published this sort of work all over the place, so it's not hard to get it accepted.
Okay. Good. Okay, so it's good to great. I'm really interested to hear a bit of the story of how you came to do integrated history and philosophy of science, how you came to Pittsburgh, how you came to the center. Before we got on, we actually had before we started recording, we had this really nice chat about documenting the history and all these fascinating things that I really enjoyed. So let's hear a bit of the story. So tell us, John, where did you grow up?
Okay, so I grew up in Sydney, Australia. My plan was to. I love chemistry. As a teenager, I did all sorts of just a little practical chemistry in the garage. And when I went to university, I wanted something a little more practical than just the lab life of a chemist. So I studied chemical engineering. In the process of doing that, there were a number of servicing classes that I took. I took 2 classes in philosophy and 1 in history of cosmology. And I found that stuff to be absolutely intriguing. I liked the history of cosmology stuff more than the philosophy. The straight philosophy I thought was a little contrived and a little narrow. I still remember in reading John Hosper's Introduction to Philosophy. When it came to the question of time travel, he argued that if you were to step into a machine and then step out and there was Julius Caesar and everything was just like it was in something or other BC, it wouldn't be time travel because literally it was the next moment for you. And I thought, that's really dumb. I thought you've just used a definition to destroy what was really interesting. So I actually wrote a paper, a final paper on time travel. I was just interested in looking in the physics of where it could happen and what could be there. Okay.
So this was at the University of South Wales? University
of New South Wales.
New South Wales, right.
I got a job as a chemical engineer. I worked for Shell in an oil refinery for a couple of years as a chemical engineer. That was, an interesting experience. Oil refineries are enormous machines and they have all sorts of processes going on in them. And the job of the chemical engineer is to understand those processes and fix them when they go wrong and design new ones as they're needed. So that was quite exciting. But it wasn't what I wanted to do long term. And I realized you only come around once. So I thought I'd do something else. I did what many Australians do. And that is, of my era, airfares were very expensive and travel was difficult. So you would stop everything you're doing, pack all your belongings into a backpack, get a one-way ticket to, in my case, London, step out of the plane, and then figure out what am I going to do now. And so I spent a year traveling around Europe, just doing that. In the course of that year, I went to both Cambridge and Oxford, and I went to Cambridge, and I got non-member leave to attend lectures. And I spent the Easter term of, it would have been 1977, attending all their philosophy lectures and also HBS lectures. And that was an interesting experience. I discovered there that I liked HBS more than I liked philosophy. You go to a philosophy lecture knowing things, and you'd step out of it knowing less.
Right.
You'd step in knowing that other people have minds, just like yours, and then you'd step out not being sure anymore. And in the HBS lectures, they were about really substantial content. So I figured that's the thing for me. When I got back to Australia after that year off, I then enrolled in a PhD program in the School of History and Philosophy of Science at the University of New South Wales, where I did my dissertation.
Wonderful. Oh, wow. So you mentioned the brief experience for a couple of years is taking courses at Cambridge in the late 70s. So before we get into the dissertation, what was the landscape like, if you can remember, in the late 70s? I mean, what were there, do you recall any people you saw, the experiences, the moments of the time, the ideas of the time? What was going on?
Yeah. Well, I took various courses. Remember, I didn't really know what I was seeing because it was all new.
Right.
So
right.
I sat in a course on Kant's Transcendental Aesthetic, which had a little impression on me. A course on utilitarianism by someone called Harrison, which I thought was interesting, but I was not especially interested in ethics. There was a course by someone called Smiley on Russell and Frager's debate over definitive descriptions. That meant a little more to me because my background had been the following. I'd spent time in Vienna, and I'd been, my German's not terrible, but not great either. And I wanted to read stuff in English. And I found an English language bookstore, and I picked up Ayer's Language, Truth and Logic, right? Which is one of the founding documents of logical positivism. I picked up a book on Wittgenstein, which I read eagerly. And so then I went to Cambridge and heard those lectures. But in particular, there were lectures by Elizabeth Anscombe on metaphysics. And I was at this point, I had experienced through reading Ayer's Language, Truth and Logic, the elimination of metaphysics, and I rejoiced in this. This was a transformative intellectual experience, emotionally. Intellectually, it wasn't, because I had no idea what metaphysics was. I was just very pleased that it was gone. Then Elizabeth Anscombe, gave a series of lectures in which she argued it wasn't gone after all. That was the main point. And the secondary point was that she knew Wittgenstein, which seemed to come up often. I just thought her arguments defending metaphysics were facile. Maybe they weren't, because I was a true believer. And then I had one interaction that was transformative. There was somebody there, I think it was an American graduate student at the time, and we just struck up a conversation, and we talked. And he told me that general relativity wasn't that hard. Right? And I thought Einstein, terrific. I didn't know anything about Einstein, but I liked the idea of time. And so I went to the bookstore. I got a book, Atwater, General Relativity, and I started reading it. And, and that set a trajectory.
Yeah. Well, yes. Speaking about important experiences, so as I can see here, you went on to write your dissertation, "The Historical Foundations of Einstein's General Theory of Relativity." So, right. From this, I imagine this was one of many experiences that informed this. But yeah, so tell us a little bit about how you, a little bit about this project and how you approached it. What did you end up wanting to say here? What did you say here?
Yeah. Well. So I joined the School of History and Philosophy of Science. It's a small school and frankly not especially distinguished. It ceased to exist several decades ago. It was broken up and its professors were scattered to the winds. I didn't really have much in the way of good advice from anybody, so I was really stuck by myself. The way it works is you walk through the door, you're assigned a supervisor. I sat down with my supervisor, and the first question asked is, okay, so what's the title of your dissertation then? And I was floored. I had no idea whatever. I had no idea. I said, look, I'm interested in philosophy of time. Time's an interesting topic. And he said, okay, let's put down problems at the interface of physics and mathematics.
Okay.
And then I sort of didn't know what to do. And so my supervisor had written a dissertation on the history of special relativity. Not a good work, because he thought that the moral of it all was that we should bring back the ether, which is not an idea that I really felt comfortable with. But he said, special relativity is done. You should do general relativity. Okay, well, I didn't know anything, so I thought, what the hell? And, I went off, and it turns out that it was a very good choice. Because unlike special relativity, there's extensive documentation for the history of general relativity, how Einstein found it. He worked on it extensively over a period of 7 or 8 years and published fairly copiously. So I went to the library. This is before it was easy to get anything. I went to the library and tried to find all these papers. Most of them weren't there. So I bombarded the interlibrary loan office with lots and lots of requests, and they kept coming in one after another. And so my work essentially consisted of just sitting down and working through Einstein's original papers, in the transition from 1905 through to 1915, when general relativity was finished. And I didn't know that much physics, so every time I came across something that I didn't understand, off I go to physics books and learn it. One of the papers was a 1912 paper with the title of "Is there a gravitational something or other that is analogous to electromagnetic action?" And it was published in the quarterly of the Quarterly Journal of Public Health and Sanitation. And
interesting.
And so when the interlibrary loan officer handed that over to me, I remember her saying, some people will do anything to get published.
Wonderful.
I discovered later what the reason behind it was. Einstein had a good friend, Heinrich Sanger, who worked in that field, and there was a Festschrift in his honor being published in that journal, and people who knew him were contributing papers, and Einstein, being Einstein, contributed a physics paper.
There you go. Wow.
So I don't think there was anything especially distinguished in in my dissertation. I've made no effort to have it published. I don't think there's anything of value in it. It's basically a compendium. I read all these papers and I tried to weave a narrative into it. And then I tried to struggle with an enduring problem with general relativity. Einstein insisted that the general theory of relativity generalizes the principle of relativity to accelerated motion. There doesn't seem to be any cogent sense in which it does that. This is a major result that we now realize. So you've got this difficulty that Einstein is focused on this idea and he's going to make it work. Right? He thinks he gets it to work. Out comes a terrific theory, right? But it doesn't match what he thought he was getting. So it's
interesting. Yeah.
So I mean, I didn't know anything. How do you write the history of something like that? Right? It's not easy. No,
absolutely not. So, okay. So following the completion of the first big project, it says here you've worked a little bit in the Einstein Papers project. Was this shortly thereafter? Yeah.
Yeah. So that was the next thing that happened. My wife, we'd been married, by the way, while I was traveling around in Europe.
Oh, wonderful.
She came up from Australia and we got married and so on. We just celebrated 45 years, by the way.
Congratulations.
45th anniversary. Anyway,
oh, wow. Yeah.
She's an architect and she wanted to do the urban design master's program at Columbia. And so she set herself up and off she went. And so I had to follow. Yeah.
I was wondering, did you meet in New South Wales?
Yes, we met in Sydney.
In Sydney?
She was 16, I was 17 or 18.
Oh, wow. High school sweethearts.
Anyway, okay, sure. So she went to Columbia, and I had to figure out what am I going to do? So I started writing people. John Stachel was editing the Einstein papers at Princeton University Press then. And after some complication with communication, remember, no email. It was all done with letters, backwards and forwards, and letters get lost, and some of them got lost. And so it was an agonizing for me months of miscommunication while I tried to, figure out what I could do. He just agreed to host me. And that for me was transformative. So I went to Princeton, it's close enough to New York that you can commute backwards and forwards. So I lived in Princeton. My wife lived in New York and Columbia, and I started doing work in the Einstein papers. I wasn't an employee. I was just someone who was given a desk and could work, right, and do what I wanted to do. I had a few problems there that I wanted to work on. I noticed that Einstein's formulation of the principle of equivalence simply didn't match what everybody said it was. And so I started working through the archive one document at a time in order to figure out what was going on. But then I got derailed. The documents are numbered 1001, 1002, 1003, and I got to 3006. And there was this notebook that was marked as teaching notes for relativity, but I opened it because I just read all the papers. I could see they weren't teaching notes. And there was a huge problem that Einstein ran into with general relativity. He finished the theory in 1915. He actually had the completed theory in 1913, near enough. And he tried to figure out what the correct gravitational field equations would be. They are the analog of Newton's inverse square law of gravity in Newton's system. And along with the help from his mathematician friend Marcel Grossman, he had essentially figured out what they would be. But then he decided that they didn't work, right? And so he rejected them and instead cooked up a set of equations that just don't work well and published them, and that was his theory. So the big puzzle was, what happened?
You're right.
All we know is he says they don't work. You don't get Newtonian physics back out of this in the static weak field limit. And so I opened this notebook, and there was a calculation which ended up with the conclusion, that a certain term, sollte verschwinden, was the German, or to vanish. And I knew that the sollte verschwinden would mean that if this particular expression would vanish, in other words, be equal to zero, then he would get back Newtonian physics. But you could see sollte, should vanish, but he couldn't see how to do it. And so I just opened at that page. I flipped one or two pages, and there was this page. And, and I suddenly realized, whoa, this is it. This is the answer to what happened. And so this is that became my life. Right. The Zurich notebook is the record Einstein's struggles trying to discover general relativity, what went wrong, and from that we could then eventually figure out what went right. So I worked very hard on that document, reconstructed as many of the calculations as I possibly could, and then put it all into a big paper, How Einstein Found His Field Equations, which I then had trouble publishing because it was too technical, but never mind.
So this is your work and the trio of scholars, John Cubed. Is that what you refer to as?
That's a spin-off that comes later.
Okay. We're getting ahead of ourselves.
That comes out of that work. That doesn't happen for several years more. So that's the paper that established me amongst a tiny group of scholars who recognized that I actually could do something useful. Yeah. And that's what eventually got me a job. I got appointed at the University of Pittsburgh because, on the strength of that paper. And I mean, it was just sheer luck on my part that I happened to have exactly the right expertise, so I'd know what I was looking at, and that no one else had worked the document yet. The document was just sitting there; no one had worked it, and then I worked it, and then wrote it all up, and it then became a major industry. Right? There's now a 4-volume Springer analysis of this. Jürgen Wren at the Max Planck Institute in Berlin started an annual meeting where we all got together and we projected the pages of this notebook up on the screen, and we just worked through them one at a time to try and figure out how best to describe this. So there are 4 volumes on this. And so I basically got lucky and got it on the ground floor. I think there's always something like that. The first person to strike out in a particular direction, and then it works and it takes you get this status. Same thing happened with thought experiments. I was coerced to write a paper on thought experiments by Jerry Massey. I didn't particularly want to, but he was very senior and I was very junior, so I agreed, and I just wrote down what I thought was obvious and what I still think is obvious. But because I said it first, right, it's now one of the landmarks in the literature. Everyone, you either agree or disagree with it. I didn't do anything especially clever. I just did it early, before other people wrote on it.
Oh, I see. You're well known for your own thought experiment as well. Yeah.
Oh, which one is that?
Norton's dome.
Oh, that came very much later. That's a fascinating story. How that kind of took off. Turns out that there are very simple Newtonian systems that are indeterministic, right? You get this dome, a particular shape. You put a mass on top. You make all the normal sorts of assumptions about smoothness and no friction, and it's a point mass and so on. And then you ask, what's going to happen next? Well, all our Newtonian intuitions say nothing. It's just going to sit there.
Sure.
Right? But it turns out that if you set up and solve Newton's equations, there are other solutions in which the particle spontaneously sets itself into motion. It's trivial. The mathematics is 2 or 3 lines of calculus. There's nothing deep in it. It's always been there. It's just no one's thought to write about it because no one's thought to look for it. At least that's what I thought. I wasn't really sure about that, but Maurice van Strain, a Dutch philosopher and historian of physics, found that a Frenchman by the name of Boussinesq in the 19th century had also found it. So you get this weird reaction to this. It was part of a paper on causation. I wanted to make a fairly small point about causation. You get this weird reaction to it. Some people just say, oh, yeah, okay, fancy that. Other people are outraged and think it is a defense against something that matters, and they're determined to stamp it out. And so there's this huge literature come up. There's a Wikipedia page on it. There's YouTube videos. And, it's fascinating.
Yeah.
There's very little in it. And it's very easy to understand. Now, what's interesting is it's not the first example in the present literature of indeterminism in Newtonian physics. If you allow infinitely many masses to interact, right, generically the system is indeterministic. And, so the example that I worked on is this: mass, spring, an infinite chain, right? If you're thinking, that sounds familiar. Yeah, it's the model of an infinite crystal, an infinite one-dimensional crystal. With a bit of fancier mathematics, you can demonstrate that system will spontaneously spring into life. So what's going on? But because there are infinitely many masses involved, people think it's not, it somehow isn't to be troubled with. But the difference with the dome is it's incredibly simple. Dome shape, point mass, calculations are 2 lines that anyone with entry-level calculus can do, and you've got the result. That's much later. We're talking about
We jumped ahead about a couple decades. I just happened to see on your wiki that and you were mentioning in the thought experiments. This was later or discussing reference to arguing just the philosophical way about the nature of thought experiments. So some almost like a meta-philosophy like paper discussing. Thought
experiments are just picturesque arguments, and they can only do what arguments can do. And a good thought experiment is a good argument, and a bad thought experiment is a bad argument.
Simple.
Who would disagree with that? I mean, that's just what the answer. An enormous literature is convinced that there's something more, there's something special about thought experiments, and we need to figure out what it is. The extreme version of that, the bookend, as it were, to the literature I have, I'm one bookend, is Jim Brown he was at Toronto, he's now retired. He argues that there is something special to a thought experiment. What happens is that the laws of nature reside in Plato's heaven, right? And a good thought experiment of a particular type opens the window to Plato's heaven, and you can literally see the laws of nature. Now,
beautiful.
Yeah, depending on your inclinations, it's either crazy or appealing. The hook is, in a good thought experiment, there always comes this moment when you say, "Oh, I get it." Right? I get it moment. And it doesn't feel like you've done something mundane. It feels like something special has happened. And that's the hook. If you feel that, then you start to wonder, well, how can I make sense of what just happened? And there's really no viable intermediate between me saying, well, nothing extraordinary happened, you just ran an argument, and Jim saying, something weird in the metaphysics has just happened, right? And let me give you an underpinning for it, Plato's theory of ideas, right? There's nothing in between that I know of that's stable.
Right. Yeah, no, I haven't followed the debate very closely, but I think I tend to lean a little bit more closer to your position, but understandably so.
You asked about the 3 Johns, so let me
sure. Tell us a little about
briefly. That. After Einstein had published the wrong theory, right, he was a guy with a big problem because he knew something was wrong. It was a little bit like Newton publishing all of Principia and writing in it that, well, we could use an inverse square law for gravity, but it's not going to work. Let's use an inverse cube law, right? The parts don't fit together properly, right? And Newton would have known it and would have been unhappy. Einstein knew it and he was unhappy. And so he spent a lot of time trying to convince himself that everything was okay. No, it's not okay. Yes, it's okay. No, it's not. And this went on for several years. Yep. In the middle of this, he found an argument that he thought would establish that what we now think of as the correct theories, these are generally covariant theories, these generally covariant equations rather could not be the right ones because they violated determinism. And this was the whole argument. It was devoted to disputing the idea that the sort of equations that we now use are actually usable in physics. It lived on purely as a piece of history of science. I think it was John Stachel, who was the editor of the Einstein papers, also a very good philosopher, who realized that there was something of deep philosophical importance going on there. And so he wrote about it. When I came to Pittsburgh, then after I was there for a couple of years, John Norton got hired. And he also had looked at this stuff. And so at one point he said to me, look, there's something really interesting going on here. We need to write a paper about it. So he and I got together and wrote a paper on the whole argument. It's called The Whole Argument. And we took Einstein's argument and took the structure that it uses and just applied it to a modern context. There's a view, space-time substantivalism, which says that space and time have an existence independent of the matter that's in the space-time, and depending on how you interpret the terms, this argument then becomes a refutation of that view. What we did was we were able to write the paper in a very punchy and provocative style. We just do what philosophers do, saying, here's the claim, here's the argument, right?
Yeah.
That kicked off a fire. So there are the three Johns: John Statchell, John Norton, and John Norton, right? And so you say, I wrote the Stanford Encyclopedia article on this, and that you might see the three Johns there. So again, it was a matter that we were lucky, because what had happened was that a new generation of philosophers of space and time had emerged. They had developed fairly sophisticated mathematical skills, but they were running out of problems to work on. And so this suddenly became a problem that they can work on. You couldn't read it without having a reaction. It's like the thought experiment stuff. It's so simple and so sharply stated that you either love it or hate it. And you've got to react to it in some way. And so, for the next 10 years, there was this intense churning of papers. What's the right way to think about it, the wrong way? It continues today. There's a lingering literature on this. It's been revived recently by, I think Jim Weatherall wrote some stuff, and then other people are disputing it. Brian Roberts says, no, you're wrong. And I just have a note in my diary that Tushar Menon is giving a talk on this on Monday.
Oh, wow.
I think it's at the Black Hole Initiative. I can't remember. At Harvard, it's a Zoom thing.
I've heard of that. Yeah, no, yeah.
I'm just going to sit in and see what he has to say. But it lives on. It lives on actually for a very general reason, and that is, do you know what a gauge freedom is in physics? I don't know if this means anything.
It's been a while, but I think that the term sounds familiar. But
a gauge freedom arises when you have a structure that does not correspond to anything in the physical theory. So think about Newtonian gravitational potential. All that matters are the differences of potential, because that gives you the forces. The value of the potentials themselves don't matter. The difference can be between 100 and 110, and that 10 difference is all that matters. And it's the same as if you had 200 and 210. Right? So the question becomes, how do you identify when you have a gauge freedom? Right? And there are only two ways, and those are the two ways that are used in the whole argument. It's because there's a difference that makes no observable difference. This is a verificationist problem. Or it might be that the freedom that you have with the gauge quantity is such that the equations of the theory can't fix it, right? So whatever's going on is somehow, the differences are invisible to the equations themselves. They say, I don't care whether you give me 100 or 200. All I care about are differences. Right, so those are the two criteria. If you get this verification problem, no observable difference, or if the equations can't determine definite values. Right? Okay. And so that keeps coming back because one of the basic questions always in physics is what truly represents physically and what is simply an artifact of description. And gauge quantities sit right in the middle of that. And this is how you figure out what the gauge quantities are or aren't. And now the key question is are these physical or mathematical principles? I think my view, and I think the correct view, of course, is that they're physical principles. There's no logical necessity for us to think that the absolute value of Newtonian potential corresponds to nothing in the world. It could, it might. It would be strange because of the various reasons we've given, but there's no logical necessity that precludes it. Anyway, so those are the three Johns.
Fantastic. So this is a fascinating story. How some luck and things have birthed like a tremendous amount of insight or interest in these particular problems. So you mentioned, because of this, you got the job at Pittsburgh. You've been studying, teaching, developing a number of different ideas and work, primarily in Einstein. You've become an authority on Einstein. Only because people who know more are dying. So last man standing, as it were. Well, yeah. So tell us, I'm always interested in how folks approach to the field and what it is they do. How do that develops or changes, just as their interests have developed or changed. So, as in working in this kind of in this field as a historian of physics, I guess at the time, how did you see yourself? Were you a mainly philosopher of physics, historian of physics, a scholar of Einstein? Like, how did you see yourself, and how did you approach doing what you did?
Motivation has always been philosophical.
Yeah,
I want to know how it is that we know things about the world.
Yeah,
right? And that's the topic of epistemology. I've always been disappointed by the traditional literature in epistemology because it's focused on questions like, if I sense a green patch, am I authorized to say there's grass there? And I'm thinking, okay. I'm more interested in this question. Given the data of experiments and observations on planetary motions and bodies in free fall, how do we figure out that gravity is a curvature of space-time? That seems to me a far more interesting question. So I was working on the Einstein stuff, wanting to know how we come to know these things. Yep. And that for me has been the issue. Now, interesting thing about most of the people who work on Einstein, at least in my community, they're philosophers, not physicists, not historians. With some very notable and important exceptions. Historians tend not to really want to focus on the intellectual content. Right. They want to focus on the social context and all sorts of other things. You need to have a particular interest. I want to know how we find things out. It's a philosophical question. So I go to the history to answer that philosophical question. And that's the sort of stuff that's then carried me through. So I moved into, issues in philosophy of space and time, trying to figure out how we know, what's the basis of that knowledge. And that you'll start to see in my CV increasingly numbers of papers that tackle issues just in inductive inference and evidence. I entered the field at a time when sociological constructivist views were taking root, and I thought they were just crazy. No doubt there are cases when sociological factors have been determinate. These are destructive aberrations.
What might be an example of some of those in relation to philosophy of space-time physics that you saw around the early 2000s?
The major trend of this was the Edinburgh School in the Strong program in sociology of knowledge. The idea was that the content of scientific theory is sociologically determined. In my area, the Foreman thesis was one of the major touchstones. In the 1920s, quantum mechanics emerged, and what was disturbing to many people at the time was that it was indeterministic. Right? And so at the time, determinism and causality had been identified. To be causal was to be deterministic, and then you get an indeterministic theory, and causality is lost, and it was a lot of gnashing of teeth and so on. So Paul Foreman argued that this was a reflection of the political turmoil in Germany in the Weimar Republic, right? That the physicists were presenting things this way because it was consonant with what people saw in society as a whole. I think the best answer to that was, if a result is determined by external social factors, it won't persist. It's still here 100 years later. The Weimar Republic is something no one knows anything about. If you want to contrast that, the classic contrast is the Lysenko affair. Right? The biologist Lysenko in Stalinist Russia brought back essentially Lamarckian ideas about evolution. And was in charge of all sorts of agricultural stuff under Stalin, and precipitated a famine, and a lot of people died. Of course, when the political pressure was off, the biologists in Russia could come back to ordinary Darwinian evolutionary ideas. Didn't survive because it was socially determined. Right. If it's socially determined and you change the social context, it's going to go away, and that's what happens. I mean, that's the thing about science. It is independent of social context. It's the same periodic table of elements, whether you're in the US, in China, in Iceland, or I don't care where you are, right? there's only one periodic table of elements, and you just can't mess with it. It's not socially determined.
It's interesting to hear the history or folks who have actually been through this. Younger scholars like myself. It's just we weren't there. Well, we were there. We just weren't paying attention necessarily early on to these debates, and so it must have been a real experientially. It must have been interesting to really be around when these ideas were coming or taking hold of the program.
There's this underdetermination thesis, which is the basis of so much work, and it's at best speculation and more likely just wrong. But it's presented as an ultimate truth about inductive inference. It's this truth that no matter how hard we try, evidence can never pin down definitively a theory, right? And it completely flies in the face of everything we see actually happening in science. Right? There is only one periodic table of the elements, and as long as you restrict yourself to large objects, ordinary size objects, and ordinary motions like planetary speeds and so on, it's Newtonian theory. There's no other theory that works. Right? And go to the very fast or the very small, and then of course things break. So I wrote about that, and you'll see me complaining various times about why this is I mean, it's a maddening thing because, I work a lot in inductive inference, and the arguments that support it are fragile as anything. They depend upon very naive hypothetico-deductive ideas about confirmation, that if a hypothesis entails true evidence, then the hypothesis is confirmed. So if we have two hypotheses, both of which entail the evidence, right, then we can't pick between them. No, you can pick between them, and it's not terribly hard. You can. So, for example, there's traditional geology, which tells us that the rock strata and so on are very, very old with their fossils. And then there's the alternative theory that says the rock strata were created 10 minutes ago, right, complete with all the fossil record exactly as they appear. They both have, by construction, exactly the same deductive consequences. And so they have the same, so by that theory, you would confirm them the same. But one of them is massively defective and the other one is not. I mean, you can see the, created 10 minutes ago, one is completely parasitic on someone else's theory, and also has this completely uncontrolled number, which is the time at which this happened. There is no evidence for when this creation moment happened, and there can be no evidence for it because by design, the theory is set up so that time is invisible. You could also say 20 minutes or 100 years, and there's no way to determine when the great event happened. Compare that with a theory about the formation of the Earth. Now, this is just regular astrophysics. When did the Earth cool sufficiently so that rock strata were forming, right? We get histories of that. We get evidence, conjectures. You get evidence for this. And it turns out to be wrong. You do that. Anyway, and then there's more wrong with the thesis. But anyway, I wrote papers on this. You can read the papers.
Yeah. We're getting into the later. We'll be talking about your book in a little bit, but I know. So it was in the 2003 paper that you wrote, introduced this material theory of induction. So what did you find to be probably the most significant about this? How did it impact others? How did it could you say a little bit more about that?
I'll tell you where it came from. I work in history and philosophy of science. I'm interested in evidence. I'm interested in theorizing, and I want to be able to go back and say, yes, Einstein had good evidence for this proposal. He did not have strong evidence for that proposal. And for that, I need some kind of an account of inductive inference. How strong is this support for that? Now, there are no shortage of accounts out there, right? All different, if you've got my CV in front of you, you can see in 2005, I wrote a paper called A Little Survey of Inductive Inference, because there were so many accounts out there. I had to find.
Yeah, they do a taxonomy of sorts.
Just for organizing them. But the problem with it was that none of them worked very well. Right? You could always, either they just didn't fit, or you could contrive a fit if you're a Bayesian. you just work terribly hard at suddenly all of these prior probabilities fly in from who knows where, and the likelihoods fly in from who knows where, and then you write down Bayes' theorem. Or if you're an IBE person, you say, well, this is the best explanation, but don't ask me to tell you exactly what explanation is, and don't ask me to tell you what it would look like if it all didn't work. And so I was just dissatisfied with all of the theories. I couldn't apply them. They just didn't work. Right?
You had to come up with your own.
It was a Procrustean fit. But then I looked at what actually happens, and scientists themselves don't think in terms of abstract formal schemes. They think in terms of facts. Here's a simple example. Since Aristotle, we have an argument form known as analogy, right? If this is like that in this many properties, then it'll be like that in the one remaining property, right? Sure. You have this abstract scheme for it, and huge difficulties in applying it because there's so many examples where it doesn't work. So, sometimes analogies work, sometimes they don't work. A whale is like a fish in almost every aspect, except it happens to be a mammal, right? There are huge numbers of counterexamples, so it never works reliably. So then I go to look at what the physicists and scientists are doing. They don't treat analogy as an argument, an abstract argument form to be excavated from a book. They treat analogy as a factual matter, right? It is a fact that such and such. When I was studying in engineering, for example, I was eager to get to some kind of deep foundational basis, and I was assured by my professors that this would come with the so-called Reynolds analogy. And the Reynolds analogy turns out to be a factual statement that the transport of heat, momentum, and matter are all governed by the same rules. But it's a fact because the mechanisms that are doing this are similar. Right, but the key thing is it's a factual statement that can be investigated independently. Or the liquid drop model of the nucleus of an atom from the late 20s, early 30s. This was again a fact. And so, how do you put the two together? Well, the basic idea of the material theory of induction is that what authorizes, what warrants an inductive inference is a background fact. It's not an argument form. So it's the fact of an analogous relationship that warrants the inference, not that it has a certain formal similarity. Right? And the basic idea behind the material theory of induction is that it's like that everywhere. Wow. So if you want to apply that to the familiar case of Bayesian analysis, I don't object at all to reconstructing probabilistic inferences using inductive inferences using probabilistic ideas. But there has to be a positive background fact that warrants it. So if, for example, you're in some legal issue and you're trying to figure out how likely is it that this culprit is the one who left that sample, right, of blood, and you do DNA analysis, well, you have lots of statistics on the frequencies of particular genes or whatever it is that they work on.
Sure.
And so out of that, you can get probabilities, and that's perfectly fine. But if you don't have the fact to justify, right, the use of probabilities, you very quickly fall into fallacy, right? And so you always, I'll give you an example of one, but the moral is before you use a probability anywhere, display what the fact is in the background system that justifies it. And if you don't do that, you commit terrible fallacies. There's one that you might have come across. There's a huge literature now that suggests that very probably we are living in a computer simulation, right? So where does that come from? It comes from exactly the fallacy I just described. So the argument is, well, in the future, advanced civilizations will be able to simulate everything, right? And blah, 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 blah. And then all of this is a bit shaky, but it ends up with the conclusion that think about the ways that we could be physically real, right? Quite a few ways that could be, but think about the ways that we could be simulated in a computer environment. Since computers are so much more flexible, there are vastly many ways that this could happen in a computer. Okay. I don't know if that's well established or not, but you could just stop.
Seems like it.
And who the hell? Yeah, you've got nothing. Yep. To get something, you then have to say, we don't know which is the case. right? You have to be ignorant. We don't know which is the case. Okay, well, I have a feeling I know which is the case, but let's set that aside. And then you have to say, I'm going to represent my state of ignorance probabilistically, right? And so I'm going to spread my probability roughly uniformly over all of these cases. And since there are vastly more simulation cases than there are real cases, virtually all the probability goes to the simulation case. Therefore, very probably we are in a computer simulation. What's appalling to me is that this idea has been taken up, and you see YouTube videos on it.
Right.
I've even seen Scientific American articles in which they take this manifest, appallingly bad argument and just support it. When you think about it, where do these probabilities come from? If you don't have probabilities, all you have is the premise that we don't know whether we're physically real or a computer simulation. It doesn't really matter if the
probabilities aren't based on any particular. Yeah.
You shouldn't really have gotten to that point, because if you really think about what's involved in simulating something in a computer, you realize pretty quickly the resources that would be needed to simulate even our conversation are massive and immense. So it's not that plausible that, that such a thing could be, let alone that there are so many different ways of doing it that it's going to get all the probability. But anyway, so that's the sort of thing that can go wrong. And, that's a really clear example to see. And I feel like as you mentioned that and described particularly what's wrong with that, I've just come across a number of different kinds of arguments that have followed that path that you see usually on, a number of things. So I call that the inductive disjunctive fallacy. There are many more examples of it. I can give you more examples, but that one's interesting because it happens to have such popular currency.
Yeah. Well, there's something about it that feels, like many fallacies, there's something that it could feel right in some way, but it doesn't feel, or it feels in some ways, believable. But,
I'm not an enemy of things formal. I still do lots of work in, foundations of physics, lots of thermodynamics, and statistical physics, which is all probabilistic. And I think probabilities in the right place do magical stuff, right? What I don't like is formalism for its own sake when there's no clear point in doing it, right?
Yep.
And because what happens is you lose track of the real case. And you waste all your time, playing around with mathematics. It's very entertaining. You enjoy the mathematics. The culprits who are doing this mostly now are Bayesians. The Bayesian literature is really losing and has, I guess, lost contact with what's going on in real science.
Would this be more like formal epistemologists or folks?
Precisely.
Because you mentioned the thing of kind of describing historically what you were interested in, more so less about the green grass and more about actual, how do we know about these particular theories in physics? So what is, if you wouldn't mind sharing, what has been your relationship with the epistemology community, formal epistemologist? Has it been a back and forth? Has it been, cordial? I imagine there's been some debates. I'm curious. Yeah, what has that been like?
We got on very well.
Okay.
You've got to understand, philosophy is a discipline which we dispute, right?
So it's gonna happen.
That's what we do. We don't hate each other, right? We got on very well. So
sometimes
let's just talk about thought experiments for a moment. Jim Brown and I are the best of friends, right? And it's somehow wonderful that between us, the literature sort of lives by kind of finding a place between us. So we get on very, very well. In the case of Bayesians, Stefan Hartmann, a guy I know very well. We got on very well. Intellectually, we disagree quite profoundly, but fair enough. So for example, Stefan Hartmann, Jan Springer, and what's the guy's name? I'm losing it now. They've recently published books on Bayesian philosophy of science. I'm embarrassed. I can't remember the third guy's name. Anyway. And so they had a PSA symposium set up for the 2020 PSA, and they were worried quite correctly that it would look like it was just a celebratory fest of their books and not a proper debate. And so they invited me to join them, and I would be the naysayer. And that event went off. Of course, the PSA 2020 was cancelled because of COVID, yeah. But it happened as a virtual event. I know it was a year ago now, and so they had their say. I had my say. So our personal relations are cordial. I get them to come and talk to me whenever needed. And what is their reaction to me? The reaction is the following. They tend to be dogmatic. They know that these probabilistic methods are the right way to do things. Right? And as a result, if someone disagrees with them, well, they're wrong. And so why would you waste time thinking about them? That seems to be the attitude. It's a bit like, the circle can't be squared, right? Sure. But if your neighbor says, I've got a proof I can square the circle, you'll be polite, but you're not going to waste any time looking at the proof, right? It just, right. It's going to be big and complicated, and what a terrible waste of time. I think that's the attitude.
Oh, okay. So, I mean, personal relations, I'm happy to hear, but yeah, I was curious, more so of if there are, in terms of, it seems like the work is, there can be commentary, but there's not a lot of integration in terms of working. You're kind of working in different domains, working on similar problems, but not necessarily. I mean,
I'm working on it. If you look at the later chapters of the book, it's basically designed to argue that the Bayesian system doesn't work. There are two main claims. The first claim is that there are perfectly cogent distributions of credences, if you like, that are simply non-probabilistic, and I give examples of them. You can cook them up out of physical problems. So the dome, for example, in the case of the dome, the particle is going to move at any time, whatever. There are no probabilities in the physics. And if you try and graph probabilities onto the physics, you have to add to the physics. You've got to give a time of decay or something, right? A time parameter. So there are plenty of, it's easy to demonstrate that there are lots of perfectly well-motivated relations of inductive support, if you want to go the objective way that I prefer, or credences that are non-probabilistic. That's the first point, easy to establish. Lots of examples. I've got chapters full of them, right? The second argument is that the Bayesians have arguments for the necessity of probabilities in various forms. They are all circular, right? And it's not hard to see at a general level that they're all circular. It's because they are deductive arguments. Right? They can't use inductive arguments because that's the whole point. What is the nature of it? So they all are deductive. So they have premises, whatever the premises are. They're different in different cases, Dutch book premises, scoring rules, whatever you like. And then you deduce from that probabilities are the governing thing. But you know the way that a deductive argument works. The premises have to be logically at least as strong as the conclusion, if not stronger. Right? So there's a dominance argument. You're actually better off just positing the conclusion, right, than those premises, because typically you're leading yourself to more, right? Sure. Think about a Dutch book argument. You have to commit yourself to a lot of extra assumptions, including that the circumstances of a Dutch book, are capturing all that matters for many other problems. We don't know that at all. And then once you know that these arguments are all circular, it's then very easy to debunk every single one of them. You just go and look at the premises and ask, how have you buried probabilities in this? In the case of Dutch book arguments, there's an assumption that there exists a fair bet such that you would be happy to take either side. Right? That assumption is equivalent to the additivity of your credences. So I went to some effort on this because at the moment the scoring rule approach is the favored approach, and so I did a whole chapter on this. So where's the trick with scoring rules? The scoring rule approach is critically dependent on the scoring rule that you use. They use a Breyer score, right? Or more generally, there's a general expression, I can't remember what it's called. Never mind. So what I was able to show was that if you generalize the Breyer score in a very natural way, then you can get anything you like out of this. You can get exact additivity, as much super additivity as you want, or as much sub additivity. right? So the strictly proper, that's what they call it, the strictly proper rules are devised in order to give you exactly probabilities. Now, it doesn't stop there, right? Because they know that there's a fragility in the argument. So they try and present further arguments for why you have to use, say, strictly proper scoring rules or the Brier score. But it's the same problem all over again. You just got new premises, which, and so it's easy just to go to the new premises and find out where you're smuggling in the result. So that's what's wrong. There are many ways of treating the same problems non-probabilistic, and you have to treat them non-probabilistically because physical constraints will demand it in the examples that I cooked up. And second, all of these arguments are illusory, right? They're all circular, all the arguments for that. So you can see how much this sort of stuff pleases Bayesians.
Yeah, so what I hear is definitely a reaction to some of these, and a motivation to tackle and address these particularly these issues as you see them. And you mentioned, in the book, to give a more formal introduction to it, your book, titled by the same name of the 2003 paper, The Material Theory of Induction, from the British Society.
It's BSPS Open. Yeah, no, it's
BSPS Open. So if you're listening to this and you're interested in the book, it is available currently free for download, I believe, or access.
Forever. It's
forever. Yeah.
One of the things that's been missing in philosophy of science is an open access publishing house, and so a group of people, David Terra, Brian Roberts, got together with a committee and started an open access publishing house in collaboration with the University of Calgary Press. And it's BSPS Open. It publishes monographs in philosophy of science. They are open access, so you can download PDF wherever you want. And that was very important to me to publish in an open access publishing house. Let me tell you why. First, I think open access is essential to the future of scholarship. Right? We need to get our material as accessible as possible. I don't do the world any favors if I publish something behind a paywall where the amount to pay to get in is so great that most people can't afford it. That's the first reason. The second reason is purely selfish. If you want your stuff to be read, publish it open access. Because then anyone who wants to read this book, if anyone's listening now, 2 or 3 clicks on your website, you've got the PDF on your desktop, and it's available for you to read. The general experience is that when you make a shift from closed to open access, your readership jumps by a factor of 10. So for purely
that's incredible.
You want to be read, publish open access.
That's incredible. There's been high praise for the book. It has, looks like it's a very big, it's a very large volume of sorts, all kinds of interesting chapters, to address problems of induction, and issues related, replicability of experiment, power of inductive inference. Yeah, all kinds of, also, so has this been like a long, this is a meaty book. Is this something that has been in the works for a while, or is this something that where you've weaved together, some prior work and kind of have come back to it to return, or
it's virtually all new work. I wrote it over the last, maybe decade. I just started writing chapters and put them together. Until I collected enough. I'll tell you 2 things about it. The first thing about it is it's an HPS work. If you look at the earlier chapters in particular, lots and lots of historical case studies, because my concern is to talk to real examples in the science. So I start out at the beginning with the example of Marie Curie, who prepares 1/10 of a gram of radium chloride and then declares that radium chloride has such and such a crystallographic structure. It's a massive inductive inference. What's going on there? And I go through the history of exactly what she's doing, and it has a material basis. It's not an enumerative induction. It's something else. And I go through lots and lots of, because that's my concern. I want an account of inductive inference that works with the real history. Now, the next question is, what's the reaction been? There's been one very recurring reaction. And it's the following. So I say that an inductive inference is warranted by fact, right? And the fact has to be a true fact. Otherwise, you've got the analog of a deductive fallacy. You have a failed inductive argument because, the fact has to be true or the warrant isn't there. But then how do you know that warranting fact is true? You need another inductive inference, and that'll be warranted by something else. And how do you know? Okay. So the question then becomes, is there a Hume-like regress there so the theory doesn't work? I have two responses to it. One response is, if there is such a thing, so what? It just means I'm in the company of all the other accounts because no one seems to know what to do with this, right? But there's a second, stronger response, and that is, in fact, that isn't the case, because the assumption when you have that regress, you assume a hierarchical structure to the nature of inductive inference, and that hierarchical structure is simply not present. The actual structure, when you look at the real examples, the actual structure consists of lots of crossings over. There's no, you can't actually map out a regress like that. All you can do for a mature science is say you've got this incredible tangled crossing over structure of relations of inductive support. And if I pick any one particular proposition in science, I can tell you exactly why it's well supported, right? And if you think, go to your favorite science and ask, so there's no element between, let me go through, hydrogen, helium, I don't know, between nitrogen and oxygen. Is that right? Yeah. There's no element between nitrogen and oxygen, right? Why do you think that? You'll get a massive story. It'll be mundane. It'll be boring, right? But there'll be huge amounts of evidence. So no, it's not possible. You can go to any particular fact in the science and get a similar response for a mature science. Okay, so that's been the massive reaction to the book. Everything I just said now is actually already said in a paper I published in 2014. It's called A Material Dissolution of the Problem of Induction. I was very worried, though, that the problem of induction is a shiny object that distracts philosophers. Once they see it, they can't see anything else. And I was concerned that the Material Theory of Induction book would just be taken over by this problem. And if the material theory didn't solve the problem of induction, it would still be worthwhile. Right? So I very consciously did not include any of that discussion in that book, right? Until the very last pages. There's an epilogue in which I say pretty much what I said to you just now. Anyway, that book got published last year. The publication was delayed after the finishing because I was waiting for BSPS Open to come online. And while that was happening, I wrote another book. And
what do you know?
The other book.
Tell us a little bit about this. This is a new one.
It's the large-scale structure of inductive inference, right? And it addresses this problem in extensio, right? It's all about, I just described for you the large-scale structure of this massive crossing over, and I look at all of its properties. There are all sorts of questions that you would ask about how inductive inference works in the large scale. If I have a particular body of evidence, since it's facts that always dictate what relations of support are, am I assured to get a unique structure out? Or think about that structure, right? You've got relations of support crossing over. Eventually, you're going to cycle back if you keep tracing them. Is this a harmful circularity? I argue no. There are lots of circularities that are completely benign, and this is one of them. It's not harmful because there aren't multiple systems that can do the job. There's only one unique system that comes out of this. And then, then I look at the problem of induction. The basic claim I wrote. There's a chapter in which I actually wrote a history of the problem of induction, which I found intriguing as a... Oh,
that would be interesting to read. Yeah.
Well, the interesting thing about it is that it faded away in the 19th century. No one cared about it at all. Hume was notorious for his dislike of religion. It was revived in the early 20th century by people like Russell and Reichenbach. And then the definitive presentation was given by Reichenbach's student, Wes Salmon. Wes was a faculty member here for years while I was at Pitt, and his book was one of my favorite books in philosophy of science. So there's I realize just how small the community is. Anyway, but
sure.
So in that chapter, so the basic claim is the following: the traditional Hume problem is set up as a problem for a universal rule of induction, a universally applicable rule of induction. What can justify a universally applicable rule? Well, either it justifies itself, which is circular, and that doesn't work because you can find all sorts of self-justifying rules that are silly, right? Or it's justified by another rule, which is justified by another rule, and you have the infinite regress, okay? So how do you defeat that? Well, the key feature is that you base your inference on a universal rule of inductive inference. I don't have them in the material theory. There are no universal rules of inductive inference. So the argument that I just set up can't be set up in the material theory of induction. The closest you can come to it is to say, well, maybe there's a regress of some sort that's analogous, but I just told you why that regress requires an assumption of a hierarchical relationship amongst relations of support, that you can stratify all the propositions of a science such that you can only justify a step from one level to the next higher up by using a warranting position that is already higher up. And that just doesn't work. So one of my favorite case studies I looked at great length is chemistry in the 19th century. There was maybe it's too complicated to go into, but it's. I'll tell you the upshot.
Well, you can give me the general overview. I mean, in terms of, I find this fascinating the way in which to test these ideas of using these case studies. Yeah, so tell us about this.
So here's just an example of the crossing over. Avogadro's hypothesis, for reasons that I won't go into, but would love to, has a central role in 19th century chemistry. It's essential to determine molecular weights and molecular formulae, atomic weights and molecular formulae, and it was a difficult hypothesis for which to get evidence independently, right? And eventually what worked out terrifically well was that people working in statistical physics modeled gases after the Maxwell-Boltzmann approach of, many hard spheres bouncing around one another, and they came up with the theorem, the equipartition theorem, whose consequence is Avogadro's hypothesis. So they were able to say, oh, look, right, we know our theory is doing well because our theory is saying that gases will behave in such and such a way, but that's just Avogadro's hypothesis. So we get tremendous support from chemistry that our approach is correct. Meanwhile, the chemists are saying, how do we support this? Well, look, over here, the physicists have come up with a model of the way gases are. So that's a classic example. This sort of crossing over happens all the way.
Yeah.
There's no hierarchy here. It's just, you get support this way, you get support that way. Now, if you're worrying, oh, that's circular, yeah, but there's nothing wrong with it. It works beautifully well. What alternative is there? Circularities are harmful when you can show either there's a contradiction, the sentence I'm now saying is false, classic Epimenides, or you can show that there are multiple possibilities. There are no other possibilities that anyone's come up with that seriously considers. All of this happened, 100 and something years ago. If there were another theory that was completely different, that didn't have those basic relations in it, we would have seen it by now. Quantum mechanics, by the way, hasn't changed anything. I know, according to quantum mechanics, molecules or atoms are little hard spheres, but the essential granularity of them and the statistical physics that governs them is still the same. So you can still run the same arguments.
Wow. So this book is done, is on the way to being open access potentially.
Yes, absolutely. If I can, I will. I've sent it to BSPS Open. I don't know if they'll like it. If they don't like it, I'll find some other way to publish it. Open access. You can read it now. It's on my website.
Oh, wonderful. No, yeah. I mean, this is something, it's for younger. Well, I'm curious of the. Yeah. So in terms of what your choices for publishing, especially for young scholars, you might have, there might be a little bit more pressure to publish with particular kinds of, publishing houses or things. And so they might not be as likely to do open access right away, but for all the reasons that you said, I think it could be very, very important for getting your work out there.
It's changing very fast. Now, I understand people think, open access publishing is not respectable. That's no longer true. I'll give you a few examples and you'll see how it works. The Stanford Encyclopedia is open access publishing. I'm one of the editors. I've been an editor since the late 1990s. When I first approached people to write articles for the Stanford Encyclopedia, they would do it as a favor, or one or two cases they would decline because it wasn't professionally valuable to them. Now, to write an article for the Stanford Encyclopedia, you score big. I remember I invited someone fairly senior. Would you write an article on the stuff that you're an expert on? And he was enormously excited and said, yes, I'm going to go and tell the dean straight away. Yeah.
Well, it is, the SEP has become this sense of where if you're commissioned or invited to write, you're essentially, there is a sense where you are now welcomed into the community as an authority on the topic, even if you're not necessarily, that's just how I think the SEP is received. If I'm reading an SEP article and someone's written it, I take assuming the article is good and their, research is good, but you've turned it into this thing where, publishing the SEP or being a contributor is like something highly valued in the field. But I've seen others have attempted to make similar like things, and it hasn't gotten off the ground. And it's been much more like they are commissioning graduate students to write them, or I don't know. There's other similar kind of projects that I think have well intent, and I think could get there. But the SEP is history of the SEP. That's just a very fascinating thing.
We'll get there. Look at Philosopher's Imprint. That's a philosophy journal. It has the highest standards. It's all open access. The journal Theoria has been open access for at least 10 years now.
Heard about that.
First tier stuff. BSPS Open is highly selective. Right? Yep. If you get published in BSPS Open, you went through the mill. So that's one of the reasons I published with them, because I wanted to to help them, get established. So I'm fairly senior now. I could publish with anyone. This is a book that anyone will take. I chose them, right? And it's not, the fact of open access is not by itself a problem. It's the standards that are maintained by the open access publishers. And the appeal of publishing open access is so powerful. If you're interested in advancing your career, you need to be read. You don't want to hide your stuff. You publish open access, you will be read by vastly more people. And it'll do you a lot more good than being able to impress someone by saying, I published in this journal that no one could read because they can't afford the subscriptions.
Yeah. Well, this might be an opportunity to address the last question, which I have asked many of the guests, which is, what do you take to be the greatest challenge facing philosophy of science, or perhaps in this case, history and philosophy of science today?
Well, I have a strong view on the greatest problem facing philosophy of science at the moment. Well, actually, there are two, and I'll talk about them. The first one is that we are losing the common core. Philosophy of science 50 years ago had a kind of unified existence. Anyone in philosophy of science could pick up papers in philosophy of science and read them. We're becoming fragmented, right? There's much less work in general philosophy of science, such as in inductive inference, the stuff that I do. Right? There's philosophy of physics, philosophy of biology, philosophy of cognitive science, and so on. And those literatures are pulling apart so that they really can't talk to each other. Even within philosophy of physics, it's starting to compartmentalize more and more. So you get people who do philosophy of space and time, people who do philosophy of quantum mechanics, people who do philosophy of quantum mechanics. Do they do relativistic quantum mechanics or non-relativistic quantum mechanics? Do they do algebraic quantum theory, or are they doing and they all sort of, it's all fragmenting, right? And I think this is a problem. You'll see the fragmentation. You mentioned the formal epistemology workshop, right? It's great because they all get together and talk to each other, but they're no longer at the major conferences because they're going to the workshop. Right? Right. And this happens over and over again. That's the first thing. The second thing that's happened is a corollary. And that is, if you work in philosophy of a particular science, you now need to have substantial expertise in that science. Philosophy of physics especially has become very hard that way. You really need, prodigious understanding of the branch of physics if you're going to work in it. And it takes a lot of effort to learn that. And what I'm seeing increasingly is that people are getting better and better at the physics, but they're losing the ability for just tight, carefully reasoned philosophical argumentation. Now, one of the worst extremes of this is the following. Our job as philosophers is to understand the cogency of existing physical theories. Do they work? Do they not work? The job of a physicist is to find a new theory. Right? That's their job. It's not our job. We can't try to find new theories because to get to a new theory, you have to be willing to entertain ideas that are very, very shaky. Let a thousand flowers bloom. They say sometimes this idea might be productive, so let's not criticize it. So a major part of what I've done, we didn't talk about this, but I've been highly critical in many publications of the tradition in physics that connects thermodynamic entropy with notions of information. It's just groundless, sloppy theory. It just doesn't work. But one of the responses I get when I mount really quite strong criticism is, yes, but it's very productive. Yeah. Well, it's not actually very productive. It just produces more guff than there was before. So I see people in philosophy of science, philosophy of physics, now starting to talk about the next theory and why this idea is interesting because it might lead to the next theory. And I think this is a very dangerous development.
Wrong way to go. Yeah.
It means the dropping of exactly the critical faculty. I mean, what is it that we do? We're very good at understanding the cogency of theoretical systems, right? That's one of the key skills. And if you have to compromise that, what's left? If you want to work on the next theory of physics, you're in the wrong community.
You need to go to become a theoretical, join physics.
Be surrounded by other people who are working on that. Whereas in our community, you'll be surrounded by people who, if it's working well, are very good on critical analysis, right? That's the wrong thing for finding the next theory. All right.
No, I really appreciate that feedback. And so the first, you speak to the problem, you've loss of the common core. Others have called it the problem of hyperspecialization, where folks are just, it's great that everybody has their own, 20 to 40 person community workshop that they can go to, but then, they just don't feel the need to mingle or to really connect, or not even in a social sense, but in any sort of professional sense with the work or read others' work and et cetera. So it becomes very fragmented. This I've definitely seen, especially coming from an integrated program or a program that really emphasizes learning the science first, a motion into being more of a creator or a generator of ideas. And this does bleed into, essentially doing science in some ways. And it's interesting. I'm curious. I'm wondering if this particular problem is maybe more prevalent in philosophy of physics or more problematic in philosophy of physics than it is in something where, I don't know, where it's even if you were doing it, it wouldn't be that big of a deal, I suppose. But I don't know. I don't want to go and say that.
I don't know either.
But I could see the issue. Especially considering a loss of critical analysis, according to you and others, could be a big issue for, just it's a loss of what has made philosophy of physics successful. And just because you're pumping out work doesn't mean it's good, and there's most of it's not good anyway. That's what I'm finding. So,
if you want to see more, I have a goodies page. You found the goodies page on my website. And
I saw a link to it, but I haven't looked at it.
And one of the articles there is how not to do philosophy of science.
Oh, I think I read this back in the day. I'm going to go take a look again.
I wrote that. I went to a PSA, maybe, I don't know, was it 2018? And I saw too many bad papers. And I realized that there's a problem. And I could identify what was going wrong in many different ways. And I just found myself sitting down saying, okay, don't do this, don't do this, don't do this, don't do this. I had this long list of ways that can, that your philosophy of science can come unstuck.
Great. Okay. Well, John, it's been fun. We've gone probably a little bit over time, but it's been so great getting to talk and hear your stories, a little bit about your work, about your new book. Anything? I guess in terms of on the horizon, what are you looking forward to for the next little while?
I'm writing a book on empiricism at the moment.
Oh, fantastic!
I'm interested. I think a lot of what happens in metaphysics now has gone off the rails completely, and I want to try and do it. I want to try and correct it. I'm calling it small e empiricism. It just says what we know is what we learn from experience. If you want to get a taste of the sorts of things that worry me, I wrote a paper called "How to Make Possibilities Safe for Empiricists," mm-hmm. And it's a pretty damning indictment of what's going on in the modality literature at the moment. I publish also on causation. It's a similar sort of idea. So it's small e empiricism because traditionally empiricism has had two components to it. One is the idea of the primacy of experience, which I favor. That's great. But the other is a skepticism about learning anything beyond experience, and that's bad. Because I do think we can learn a lot beyond experience. In fact, I'm at the moment writing a chapter on the history of ideas of empiricism. And the interesting thing is that until the mid-19th century, empiricism was a view that no one really liked. It was thought to be an extreme bad view. In the 17th century, it was identified with medical quackery being the term that they were using then.
Wow.
And it's only in the 20th century that empiricism has become a kind of a mainstream view that people are willing to respect. And I think that respect is threatened by the skepticism that comes with it. So the best known of recent versions of empiricism is Van Fressen's constructive empiricism.
Yep.
And everyone, but there was a huge pushback exactly because he didn't think you could really go beyond observations, right? And I've got a few villains that I talk about, and one villain is what I call infallibilism. It's the idea that that to know something you must know it infallibly. I understand if you're not prepared ever to be wrong, then you contract to as small a body of knowledge as you possibly can. Right, and that leads you to that sort of stuff. But it's bad for many reasons because the risks you're taking are very, very small. I don't think there's much risk in saying there are electrons really. I don't see a huge risk in that, and it also overvalues experience. We are repeatedly correcting experience against theory. This is something that's got to be taken much more seriously. Now, you got time for an example?
Sure. Yeah.
You come across the M drive. I'm going to use this in the book. The M drive is this. It's a sort of a carefully shaped copper chamber with electromagnetic fields bouncing around inside. And when they analyze it, they think there's a slight net force pulling off in one direction. So you can use it as a rocket motor because it doesn't eject any fuel. Right? And so they like to boast that somebody at NASA, I don't know, NASA's huge, somebody at NASA, I assume someone not very good, has actually set up one of these things in a device and done the measurements and found a slight residual force. Right? So there you have the observation of a slight residual force. The reaction from anyone who knows anything is to say, okay, this violates the conservation of momentum. You've made a mistake somewhere. We're very happy to correct that observation against theory, and it is the correct thing to do. We ought to say to people, stop wasting your time on this. There's some sort of error in your experimental protocol. You're getting a very tiny measurement. Very tiny measurements can easily come from spurious results. The key point again to emphasize: we take a core piece of theory, right, conservation of momentum, and say that corrects observation. Because conservation of momentum is true. All right.
No, this sounds fascinating. No, sorry, I was just reading up a little bit more about this particular the discussion related to the M drive and the
Yeah,
it's been popular. Apparently, it's not been doing so well.
It's had a good run. It's been going for, I don't know, 15, 20 years now. But
yeah. Okay. All right. Well, I'm happy to see things are going well. I'll see you around the department. But anyway, thanks for joining. It's been a real pleasure. Have a good rest of the day. Looking forward to this new work and these new open access. You've convinced me that that's definitely going to be something to consider going forward in terms of publishing. So anyway,
thank you very much. I appreciate the time you've taken.
Take care. Have a good rest of the day.